as long as OBS has got the green light and you're not dropping frames, you're okay.
Okay. So I just need to grab the weekly space hangout chat. It's the only thing that's missing. So folks, can you let us know if you can see us? I'm
It's got the green light and you're not dropping frames, you're
now
okay.
Oh, I'm
Excellent.
hearing
Okay.
us twice. So clearly this is
So,
working.
yeah.
I just need to find the offensive screen. Can you say something, Fraser?
Can you hear me okay?
I can. I don't know if they can.
I could before you did whatever it is that you did. I heard myself.
Okay. Cool. Um, okay.
All right. Uh, how's it going?
It's a bit harried. I completely forgot due to telecons erasing my brain that I was producing this today. So thank you everyone for your immense patience. I'll have the weekly space hang up chat open in just a moment. Um I'm just finishing up the mad let's rearrange everything. Um
How was Australia?
Australia was fabulous. I was so sad to have to come home. I've determined that wombats are a weird cross of groundhogs and black bears.
So
Like
you saw one in the
aesthetically.
wild?
Yeah, I saw two in the wild.
Wow,
Yeah, wombats are
great. We
cool.
saw kangaroos and we saw platypuses in the wild.
You saw platypi in the wild.
Platypi? Yeah, yeah. They were adorable, but they're really tiny. They're like little ducks
Yeah.
and swimming around in a river. And you don't see much. You just see these little wakes and these little faces moving around in the water. But yeah, no, it was great. It was great. I really like Australia. And in fact, part is that you don't want to make the trip, the return journey home because it's like 17 hours.
Well, and you arrive at least when you're coming back to LAX several hours before you left. And I ended up with 2 Mondays, and I
Yeah,
deeply resent having 2 Mondays.
that's awesome. You had to experience
No,
Monday twice.
it's not
Yeah.
awesome. It's terrible. It's absolutely
Oh.
terrible.
But if you'd gone on a Monday or like maybe a Sunday, you could have made a whole Monday disappear. So,
I lost a Thursday on the way there.
right. Oh, no, that's
And
not fair.
no,
That's not a fair trade.
no, it
Um,
really isn't.
so I am in Texas
Yes.
at my daughter-in-law's wedding, and the weather is terrible.
Oh
So
no.
it's been pouring rain here. I'm sure the Texans will know. Yeah, just pouring rain. It's just been awful. And the forecast is for pouring rain for the wedding. So
Oh
yeah,
no. It
yeah, it's
is
gonna be a little
daughter-in-law taking it all okay?
no, no, she's pretty sad. And it's great because everyone is telling her, like, oh, that's not what matters. What matters is that you love each other, and and all your friends and family are going to be there again. Have this meaningful moment. And she's like, no, I had barbecues planned, and it's a great. It sounds like it's good. Like the ideas were great. She's got two taco trucks coming. It's gonna be this outdoor wedding in like like an outdoor. It's almost like a forest barbecue place. This is a big thing in Texas, anyway.
Yeah, yeah.
And then yeah, and so then there's going to be like barbecue pits and taco trucks and drinks, and then they're going to do the ceremony, and then we're all going to hang out and have a great party. So no, no, she's the whole way she had planned is now directly running against Mother Nature, so it's not going so well. But yeah, so she's anyway. It's stressful, and I wouldn't ever go through that again. That kind of making a big crazy wedding.
Yeah, my great grandmother
One.
used to always say terrible wedding, fabulous marriage. And we had
Oh, okay.
enough things go horrible on the day of our wedding that I'm just going to embrace that concept. So feel free to pass it on to your
She's heard
daughter.
that also,
Okay.
and that is no help. Yeah, yeah. Rain on your wedding day. It's luck. No, it's not. Not good luck. It's bad luck. In fact, the weather here has been almost like I don't think people have seen weather this bad. It's been this amount of rain in this amount of time. They've been having flood warnings. They've exceeded a couple of records. Yeah, it's pretty crazy here actually.
That's
So
not good.
it was much nicer when I left Canada. Nice sunny days. It was good.
That
Uh,
is such an odd concept.
yeah, it's such an irony.
So
Chris, you
so
were.
folks are saying you're a little bit soft, and I kind of agree. Can you like eat your mic slightly more?
I can't because it's on my computer. So
Oh,
either you can turn the volume higher in
okay.
your.
So
Welcome
so
to my
I
world.
you're all the way
Yeah,
up.
but you can overgain. You can put me to like, or you can decrease your volume, but you
That's
can
what I
you
just
can
did.
make it like 110%.
So everyone, you're gonna just have to crank your volume up, but hopefully the two of us are now at the same
Balanced.
level. And Gordon,
Yeah.
what glass ball are you talking about? The one in my window, Gordon? It's behind the closed curtain. So I have a bird feeder that looks like a glass donut in the window behind me that apparently is being missed.
Yeah. All right. So, if anyone's wondering what it is that they've stumbled into, we're going to do an episode of Astronomy Cast. We're going to take about half an hour and talk about space. And then we'll stick around for a little bit and answer some questions about space and astronomy. But I can't stick around too long. I've got to go run a bunch of errands. So, let's get right into it.
Okay. I um Oh, Gordon, it's out of frame to the left of the fish tank that you see in the corner. I will work on getting it in frame once I'm done cleaning. They're asking where the Astronomy Cast 500 glass bauble is.
Oh, I think I showed mine off in one of the shows last week. But yeah, I've got my shirt handy right there with it that everybody signed, but I showed it in the weekly space hangout. I haven't showed it in the astronomy cast yet.
Yeah, my house is still a wreck. Okay, so I have Audacity. I don't have Audacity using the correct microphone. Now I have Audacity using the correct microphone. You have your H4n.
Yep, I'm recording.
That device still just ugh, I hate it. Don't go through them on with it. Okay, so I'm pressing record. Hello, Chad.
Hello, Chad. All right, here we go. Astronomy Cast, episode 502. How do we know what something is made of if we can't touch it? Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain, publisher of Universe Today. With me is Dr. Pamela Gay, the Director of Technology and Citizen Science at the Astronomical Society of the Pacific and the Director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Doing great. I'm in Texas, attending my daughter-in-law's wedding, hoping for good weather tomorrow. Before we get into this week's show, I wanted to make a quick mention about a conference that's coming up that people might dig. It's called ThinkerCon. It's going to be in Huntsville. It's organized by Destin Sandlin from Smarter Every Day. There's going to be a bunch of people there, and it's pretty cool. It's like a dinner where they're going to be having dinner underneath a Saturn V rocket in the Rocket and Space Museum in Huntsville.
Yeah, Space and
So
Rocket Center.
yeah, so November 17th, 2018, from 6 to 10 p.m. And if you go to thinkercon.com, you can get some tickets. So it's about a month from now
Yes.
ish. So if that's something that you want to do, and you should check out the guests and the people who are going to be there, it's actually going to be pretty exciting. We might be there.
We might. We're still
Might.
working to sort this out.
Still
At least I am.
logistic. Yeah. We just saw a Saturn V. How cool can they be? Really cool. All right. So how do you know what something is made of if you can't reach out and touch it? How do we know what planets light years away have in their atmospheres? What about the rocks all around Curiosity or the geysers coming out of Europa and Enceladus? Scientists have a few handy tricks. It does sound like a tough one, right? You see a planet that's really far away and all you can do is look at it. How do you know what it's made out of?
It's tricky, and it all comes down to light. At the end of the day, we know everything we know about non-touchy objects by how they reflect light, how they absorb light, and how they interact with gravity. And interacting with gravity sort of helps us understand what things are made of. But when it comes to the fine bits and pieces, it really is how does the light and the material play or not play well together?
So what is this technique called? And I want to have hear you say the word so that I don't mess it up.
Spectroscopy.
Spectroscopy. And this is this method of being able to analyze the light coming from an object, and just by looking at the light alone, they can tell what something is made of. Explain how.
Exactly. Well, every object has its own unique pattern of energy levels that electrons are allowed to occupy. And as a electron gets energized to a new level, it has to absorb some energy, usually in the form of light. And every time it cascades from a higher energy level down to a lower energy level, it has to shed energy again in the color of light. When you look at a lit up sign at your local store or restaurant or bar, the color is defined by what is the gas inside that tube. So you get distinctive colors that are indicative of a specific atom where electrons are going from a level they got bumped up to by the electricity, and then they cascade down, they give off a photon, we see a distinctive color. Well, we see a distinctive color that matches that thermodynamic electrical energy level thing and stuff, and that is the brightest one that our eye is detecting. But atoms and molecules have an entire well-defined series of energies that are the only energies that our electrons are able to be in. So when we look at a rainbow, continuum light of all temperatures coming off of a warm object, and we see on top of that continuum bright lights, that means that there is an excited atom that is giving off photons. That's an emission spectra. And we can figure out what atom it belongs to by measuring out what is the pattern we see. If we see a bunch of dark lines on that continuum, that rainbow spectrum, we know that there is cool gas that is absorbing out the light from some background source. With our own sun, the inner parts of the sun emits a continuum, a rainbow of light, and the outer atmosphere of the sun absorbs out different elements, causing dark bands in that solar spectrum that we can observe.
Now, like when we look at a rainbow, when we think about that idea of a rainbow, we imagine it as this universal rainbow, that all rainbows will look like this rainbow because that's what rainbows look like. But the reality is that's just the rainbow that comes from the sun, our sun, right?
Yeah.
And so that is a custom rainbow that we get that is kind of trying to tell us what the sun is made out of, isn't it?
Well, that custom rainbow that we see with our eyeballs is just the continuum spectrum of the sun, and it is consistent with any star that temperature. So
Right. If it was a red, all I'm saying is like if it was a red giant star, if it was a blue star, we would see
yeah,
a different rainbow.
exactly.
Right.
And it
Yeah.
all comes down to which colors give off the most light and which colors give off the least light, and that where in the colors the most energy is coming out is determined entirely by the temperature of an object. So
Right.
a hot
And
blue
so
star is blue.
and that's your baseline. That's your custom rainbow that tells you that temperature of the star. But then if we take the light that comes from the sun and blow the rainbow up, magnify the rainbow, we can see what you were talking about. We can see this custom fingerprint in the light itself.
That needs to be a new Skittles line. Magnify the rainbow.
Magnify your custom rainbow.
Exactly. So when we zoom in, when we take that rainbow and we spread it out so that instead of being a few thumb widths across the sky, it is instead 30 feet wide in some extravagant spectrograph. When we spread it out like that, we're able to see exactly what's going on at every fine-grained wavelength. This is like going from that pack of 8 crayons to 24 to 128 to an R of 120,000. And with that high resolution, we're able to see, oh, here are the lines of oxygen in our atmosphere absorbing out sunlight. Here are the lines of the hydrogen atoms in the sun's atmosphere. And when we're trying to understand what something's made of, this actually makes things more complex. When we look at the moon, if we look at its spectra in detail, we are seeing 3 different things. We are seeing the absorption and emission lines that are native to the sun. So these are things happening in the sun's atmosphere that are reflected off the moon. We're seeing the colors of light that are absorbed out by the moon's surface. And we're seeing the colors of light that are emitted and absorbed within our own atmosphere.
Right.
And this all layers together where you can end up with crazy things like the sodium lamp near your observatory makes it look like the sun has sodium. And we have to know how to correct for all of these things. But
so let me just, I just want to stop you for 1 second. So when we examine, say, the light from, when we look at the rainbow and we expand that rainbow, we're seeing the light from the sun, and we're seeing the interaction with our atmosphere.
yes.
And when we look at the moon, we're seeing the light from the sun, we're seeing the interaction from our atmosphere, and we're seeing the special little bit of the recipe that the light bouncing off the moon gets added to this picture as well.
Exactly. So we have to correct for what the sun's doing. We have to correct for what our atmosphere is doing. And once we correct for those 2 things, there's chunks that we know nothing about because the lines from the moon and the lines from the Earth's atmosphere and the lines from the sun are interacting. And then we're left with a stripy rainbow of what the moon is doing.
That's really cool.
Yeah.
Now, how did astronomers figure out that each individual kind of rainbow matched the chemical? Like, how do they know that, if I see this in the rainbow, then I know that's the presence of oxygen?
Well, it was a non-linear, highly creative process. Spectrographs started to be understood. Prisms started to be understood as long ago as Herschel. We knew you could send light through a prism and get a rainbow. But we didn't understand the tie-in to individual atoms until people started doing laboratory chemistry and looking at a variety of different atoms, and then notice that if you take the pattern seen in the laboratory and compare it to the pattern seen in the stars, by golly, it's the exact same pattern, just shifted around because things in space move. And so when people first tried to understand the stellar spectrum, started to try and understand the dark and bright lines in the continuum of stars, they labeled the lines not entirely useful things like A, B, C, and D instead of hydrogen alpha or the calcium 2 lines. It took time to figure out the atomic origins. And what was kind of cool is they saw the relationship between color of star, kind of star, and the spectral lines that could be seen before they fully understood how all of these pieces fit together. This is why our stellar categories have crazy names like O stars, B stars. It's because we didn't quite know how to fully put them together when people started labeling the spectra. Once we got this combined understanding of how things vary as a function of temperature and a function of luminosity, that gave us the color magnitude diagram, the Hertzsprung-Russell diagram. But that was just the first step. That really helped us understand atoms. But when it comes to understanding rocky stuff, The story's a little bit more complicated.
So right, so and that's what we're going to go to next is like so you can figure out what a gas is made of, but how do you figure out what something, like how does curiosity know that a rock is made out of something if it can't just go over and I don't know,
Well,
lick it?
curiosity
I don't know.
does go on over and grind
It does
on the
sometimes
rocks.
and look at it very closely, but it also has a laser.
It does. And curiosity is a variety of different techniques. It can cheat and pick up a sample and run it through a mass spectrometer, and literally count up the atoms of what is inside and the molecules of what is inside a given rock. It has the ability to use lasers to heat them up. It will take spectrum, and it's that reflected light again that makes things interesting. But here we do couple things with mass spectrometry. When we look at those samples on Mars, it's knowing, oh, if I pick up this rock and I shine light on it, it looks like this. And if I take that exact same rock and grind it up through my mass spectrometer, then I see these atoms. So again, it's laboratory chemistry that tells us how to understand all of the reflected light.
Right. And so, I mean, it's such a great idea, right? That astronomers, I guess, or scientists have been burning things and vaporizing things for hundreds of years or 100 years to get that chemical signature of every single chemical that they can think of. And then when Curiosity on the surface of Mars is zapping things with its laser, they're looking at the the signature of the light that's coming back from these things that have been blasted by Curiosity, and it's able to know what they're made of.
And and with asteroids, it gets even more interesting because here what we're relying on is, oh, expletive, a rock fell out of the sky and knocked a hole in this roof. Oh, cool, let's take this rock over, shine light on it, measure the emission and absorption of the light as it reflects off of the rock, and then let's grind up a piece of it, run it through a mass spectrogram, and now we know that when we have a piece of space rock that looks in a given way, it is related to this thing that fell to the earth. And what's
Right.
awesome is we actually have pieces of like Vesta that fell out of the sky. We've been able to pick them up. And so we've ground up pieces of Vesta to measure its composition. And we know whenever we look at things that reflect light the same way that Vesta reflects light, this is what they're made of. We're
That is really
violet.
cool. So let's talk about some of the other stuff. Like one of the big techniques that astronomers are going to be trying to figure out over the next little while is there the presence of biosignatures in the atmospheres of other worlds? Is
Yes.
there evidence that there is life there on planets orbiting other stars?
Yeah.
How will they do that?
Well, first of all, here, one of the things I need to remind everyone of, because we couldn't do this otherwise, is when another star, another planet is moving relative to the Earth, we see its spectrum shifted to the blue if it's coming towards
Right.
us, to the red if it's going away from us. The reason this is important is what we're looking for is that planet is going to have a star, hopefully. That star's light will periodically shine through the planet's atmosphere. We measured the starlight. We measured the starlight going through the atmosphere. We subtract the star's light. That leaves us with the emission and absorption caused by the planet's atmosphere. So, just like we see when sunlight goes through our atmosphere, we see the oxygen lines. We see the calcium 2 lines. And actually, no, that we don't see. We see the oxygen lines. Let's just go with that one.
Yeah.
Because that other planet and star's light is shifted redward or blueward compared to ours, their oxygen lines don't hide behind our atmosphere's oxygen lines. And this allows us to look for oxygen, to look for other atoms that we have, that hopefully these other worlds will have as well.
I love this. I love this idea. We talked again about how you look at the sun and then you look and you're able to subtract the effect from the earth and you're able to subtract the effect from the moon. And so in this case, you look at the star and then you watch as the planet passes in front, and then you're able to see how the signature changes, and then you're able to subtract out, and what you're left with is the chemicals that are in the atmosphere of this other planet.
That is entirely true. And so much depends on our ability to accurately get rid of our own atmosphere. And this is where spacecraft like TESS were designed really to function with the James Webb Space Telescope, so that James Webb, out in its position beyond the moon, would have no Earth atmosphere to be looking through. Unfortunately, JWST is currently slated for the end of March 2021. We'll see if that actually happens. I am a
Yeah.
pessimist. Um,
We
and
just interviewed someone from James Webb last night, so he felt pretty confident. But,
okay,
we'll but
okay.
he was pretty confident 2 years ago when we interviewed him before. So
Yeah,
I'm
it's
sure.
dead to me until it returns data. We're just going
Yeah,
to go with that.
until it
It's dead
returns
to me
data.
until it returns data.
Yeah.
Um, so as as we collect all this data, we have to constantly correct for, well, if you're taking observations from Mount Wilson, which is at a low altitude, instead of Atacama, which is in a high desert, you're going to have more water lines in your observations because you're observing more water in the atmosphere. So this is where space telescopes are so important when studying planetary atmospheres, because otherwise our own atmosphere gets in the way. And with space telescopes, we can go into wavelengths that most molecules are really happy to do all of their happy spectral absorption and emission in infrared and millimeter wavelengths. So they're already in the red. They're in wavelengths that we can't consistently see from the surface of the planet, except in small windows that telescopes like ALMA really take advantage of. But in space, no atmosphere, no
Right.
dark places in the rainbow.
I mean, there are wavelengths that we are incapable of seeing, as you said. Some stuff in the infrared, things in the X-rays, gamma rays that we just have no way to even see from down here on Earth. So once you get up into space, you can see them at all, and then try to analyze the spectra from there.
And this
Um,
is literally a problem with our atmospheric composition going, oh, I like this color, and absorbing it out completely as the atoms or molecules become excited.
let's talk about some of the limitations then, because although it's a wonderful technique, I'm sure there are some things that it's not great for. So what are the limitations of this technique of spectroscopy?
Well, one of the most frustrating limitations is you are limited in how much you can expand the rainbow, just how fine a detail you can see by how big your equipment is and how bright the object you're looking at is. If I'm using, as I did in graduate school, a 107-inch telescope to try and get spectra of a faint galaxy that is zero point 0.3 billion light years away, uh, I can't get really detailed spectra. I can figure out what its redshift is. There's certain key lines I can see, but I can't get in there and see all the little details. When I look at extraordinarily bright stars, the kinds of things that you can see with your eyeball, because they're bright, I receive enough photons that I can spread the light out vast amounts. And not only can I see all the atoms, but I can start to see the difference between one isotope of an atom, one number of neutrons in its core, and another number of neutrons in its core. And when you're studying another planet's atmosphere, what this means is you're going to be limited in how fine a detail you can resolve by how bright that host star is. This is where TESS, which is set to observe nearby stars looking for planets, is seen as the flagship mission for identifying objects that we can, well, we can measure the atmospheres.
kind of imagine this situation where you've got like you're looking at a star field of a bunch of stars and a bunch of faint galaxies maybe,
Yeah.
and for the bright stars you can get very crisp, very bright spectra,
Yes.
and for the dim stars you've got very faint spectra, and you just can't get the detail, the resolution in that spectra to be able to figure out with a satisfying answer what something is made of.
And
And then imagine how difficult it's going to be for a to find out a planet orbiting another star, right?
and this is something that anyone who's ever used a zoom lens in low light conditions, or anyone who's done astro imaging, has encountered. If you try and zoom in on that dark field, uh, you're gonna get nothing but noise. But if you have a larger area hitting each pixel, you have more photons per pixel and you get a better image. So you can do wide field photography fairly easy in low light situations, but you can't use your zoom lens if you like yourself or if you like your images to look good.
Right.
Now in astro imaging, this is where we start referring to it as binning your image, combining light across multiple pixels where you have lower resolution, but you're able to see fainter objects.
Right. Um, which I always turn off because I don't like the way the pictures look. I'm like, nope, too low resolution. I want the higher resolution. And then I'll just let it collect more light when I'm doing
Exactly.
astrophotography.
Yeah.
So the other thing I know that is a bit of a problem is, although you can tell that there is the presence of certain chemicals, you can't really tell how much of it there is, right?
You Yeah, so there's limits. Um, each spectral line has a we call it a depth that it can have. It can absorb a tiny amount of light. It can absorb all the light in a given color. Once an absorption line is saturated, this is where all the light in that color is absorbed. You can tell nothing else. So, to a certain degree, looking at stellar atmospheres, we're able to say what a star's composition is by looking at the ratios of the depths of the lines at different wavelengths, looking to see how as a function of temperature do these lines change. We've built up an understanding of what the ratios of the lines should be, and it gets very harried, and there's lots of tracing of points and spectra involved, and thank God there's now software for this. But we can do it up to a point. Once something's saturated, you can't tell anything else. It's like, I absorbed all the light. You know, I have more of me. I could absorb more light if you had it. You don't. So once you hit that saturation point, it's like filling a bucket. The hose may still be on, but you can't tell how much water came out because the bucket's full and now it's overflowing.
Right, right. Um, but still, I mean, I think it's safe to say that this technique is like modern astronomy wouldn't be the same without it.
Oh, no. This is the most powerful tool we have in our astronomical toolkit. Photometry, which is what I do, which is measuring the total amount of light that comes from an individual object. Uh, it's powerful. You can do lots of different things with it, but it's just a tool. The spectroscopy allows you to do a vast variety of different kinds of things, measuring the temperature, measuring the composition, measuring the velocity. And when you start looking at alien worlds, it allows you to say there is life there, and potentially, thanks to pollution, there is intelligent life there.
Right. So we don't know how much, but at least we know that they're there.
Exactly.
It's an amazing technique. It's always, whenever I hear that a mass spectrometer is being added to a mission, I'm like, yes,
Yeah.
so great. Thanks, Pamela, and we'll see you next week.
Sounds great, Fraser. See you later. And now we save. Okay,
All right, I
folks,
go.
I'd love to know what you think of our new layout. I know I didn't do the Fraser thing of switching back and forth between the different speakers because, frankly, I forgot to set it up. That will be fixed for next time.
Well,
But
I'll probably be engineering next time because it's hard for you to engineer
I'm
and
getting
provide.
better at it because I have to
Oh,
do it
for
with other
sure.
shows.
I'm just saying it. Let's just make it one less thing that you have to do. But it's really nice for me to be able to travel and not have to worry all the time about it, right? So no, I
Yeah,
think it's great.
you can't do production on a single screen if you like yourself.
No, I have four screens, and it was funny. I was last night. I was with hanging out with Morgan, and we were at his house, and it was really complicated and really hard to do on two screens, and he was definitely like, okay, now I understand how this works, and but it took some doing to kind of get it, and we were still like, I'm not entirely sure why we were having some frame drops and things were a little slowed down and stuff, so it was definitely suboptimal. So I need,
Yeah.
I guess, more screens and a faster computer.
To be fair, I have two screens, but one of them is 43 inches.
That's cool. No, try four screens. That's the way. But there's mine are smaller. 43 inches is a very big screen.
It really really is. And I'm getting a complaint that I'm on the left and you're on the right. So I'm gonna switch this because I like our
We're
audience and I
backwards.
like them happy. Yeah. So currently there is chaos. Chaos is ensuing. I shall fix this. You all are now seeing the sausage being made as I move things around. Okay, so we now have Fraser in the wrong place, and I'm not there yet. We are now, I think, where the audience wants us.
Quad Libet is saying that miners here on Earth use spectroscopy to look for valuable minerals from airplanes. But as Dr. K says, it could be a sprinkling on the top or it could be a mountain work. They still need people to dig.
Yes, it's true.
Yeah. So hit us with some questions if you have any. And I'll stick around until the top of the hour and then I got a book.
Yeah, me too. So it's life.
Apparently you have radical hair.
I have what?
Radical hair, someone said. Pamela,
I,
radical hair, love it.
and this is like after it's massively faded, so it's usually much brighter.
Rainbow hair
Yeah.
just for our topic. Someone's asking what a gravity map. So John Drake is saying that gravity maps need more highlight, more limelight. Have we
So
done an episode
no,
on gravity?
that might be a good thing to do next.
Yeah, yeah.
And maybe do that and lidar to not lidar. Yeah. Lidar, sonar, all of the R's.
Hmm.
So
I mean, I would
lidar,
love the idea of
radar,
doing
sonar.
lidar, but that feels. So you're saying making that a separate one?
Yeah, yeah. So do
So
one on
gravity
gravity
map.
mapping and then one on
Yeah,
lidar, sonar, radar.
yeah, yeah. No, that sounds great.
Okay.
But
Susie,
yeah, no
you have
gravity maps.
topics.
There you go, Susie. I mean, gravity. I would love seeing the gravity maps of various worlds and talk about how they change when there's earthquakes and things like that. Um, Dustin King asks, does a single atom in a vacuum give off black body radiation?
Does a single atom
In a
No, a
vacuum.
single atom can't give off black body because black body is a result of an entire population. It comes from statistical thermodynamics. An individual atom is excited or not. That's just what it is. It has an energy level.
Yeah. So the process of an atom giving off an electron, or sorry, giving off a photon, is it needs to absorb a photon. Electrons need to go up and down a level, and
Right.
then a new photon is released. So if
Yes.
it's just in a vacuum, it can't receive the input light, and therefore it can't
Well, vacuum
get
doesn't imply no light.
right.
So
So you
so
can have,
you can have an excited atom in a vacuum. It's just all by its lonesome excited about light. Um
and it's going to give off it can give a photon of a very specific temperature,
yeah,
but it's not going to give off the black body range, right?
exactly.
I don't have access to the Slack, so if you see any questions in the Slack, let me know.
Oh, I didn't realize that. Okay. So Most recent question is, what would be a surefire indicator of water on an exoplanet? What about just indications? You look for the absorption lines of water molecules. It's just that simple. Water molecules love to absorb light, so we just look for that.
And again, that tells us that there is the presence of water on that world, but not necessarily if it's a entire world made of water, or there's just a little bit of water vapor in the, they could probably tell it between water vapor in the atmosphere. I'm trying to think, but the point is they would need to know that, like, they would have to calculate, say, the mass and density of the planet to figure out how much of it is ocean.
Yes. So we also have the question, could you tell if there was water on another planet by seeing polarization reflected off of a lake? Or do other liquids do the same? I just don't know. I think that because polarization can come from many different kinds of surfaces, that polarization alone wouldn't be indicative.
One of the instruments on board the Very Large Telescope is designed to detect the polarization from light hitting an atmosphere of a planet.
Okay.
So I don't know if it has the ability, if what would be involved for them to detect the polarization of the light coming from water as opposed to the polarization of light from an atmosphere. As you
Yeah.
said, you might just be polarized, which says it bounced off something here.
And I don't know how much an atmosphere above a body of water would mess with the polarized quality of the light.
Yeah.
Um, yeah. So we also have, how do you know that an asteroid came from Vesta or Mars? I'm going to replace the word asteroid with space rock, because asteroid, we don't have any Mars asteroids, thank God. That would have required one expletive of an impact with Mars. So when we find meteorites on Earth, we can figure out roughly where they came from, and in the case of Mars, that they came from Mars, by looking to see what is the composition of volatiles trapped inside the rock and what is the composition of the rock. So it's that combination of, does it have the atmosphere of Mars trapped inside of it, with does it look like it's made of the same stuff as Mars, that combined together tell us the rock is from Mars. Or
Right.
alternatively, that it's not and it came from some place like Vesta.
So they slice the rocks open and they smell the gas, and that's how they tell that it came from Mars, because the gas trapped in the rock a long time ago was Martian atmosphere. But with Vesta, they have to grind it up and make sure that the chemical composition of the rock matches what we know is on Vesta.
Yes.
Right.
So then there was a question. This is one that you may know better than me from your interviews. Uh, how long does it take us to fully understand all the quirks of a given spaceship?
I don't know whether we ever do. Um,
Yeah.
I mean, I
And
think, the space shuttle and then the International Space Station was pretty much the most complicated machine that human beings have ever built. And when you think about how many quirks there are in a mass produced object with a lot of quality control,
yeah.
like a car,
Yeah.
there are millions of copies of the same car, and they have a whole team of people whose only job it is to find and identify and iron out every single quirk. uh, there's going to be no way to catch up with all of those quirks in something as complicated as the space shuttle or the Falcon. I mean, the SpaceX is the closest thing to that, because with, say, the Falcons, they're making iterations on every single version of this rocket. They're changing them slightly. They're swapping out components. They're improving various parts of it based on how the previous mission went. But that was happening to some extent with, say, the space shuttle, but they didn't launch them often enough to really be able to run those real cycles. So
Yeah.
my guess would be that they have a million little quirks and they never go away, right? And they never
And
iron them out.
And with things like space telescopes, it generally takes us at least 6 months to get a stable data pipeline where everyone's like, okay, here's how you process your data. And those are going to get modified over time as random scientist acts as like, wait, I found a better way. And so it's a matter of you get your first iteration of this works after about 6 months, and then there is no point in time where you are completely done figuring out exactly how to process your data to get the best results, taking into consideration all the hardware, all the software, and all the randomness that comes from making observations from space.
Yeah, I mean, it's really important to understand that every science mission, every spacecraft is like a bespoke object
Yeah.
that some group of mechanics and roboticists are building for the first time.
Yes.
One of them.
Yes.
And so it's not even like a really skilled furniture maker who is just making you a copy of the chair that they always make, but they're making it just for you. Literally, you're saying, I want a chair for elephants. And they're going, huh, okay, all right. And then they have to figure out how to make a chair for an elephant. And then they make one, and then they'll never make one like that again. And so they are absolutely, and there's, they can use off the shelf parts for the various components of it. But a lot of times, and this is what you're getting to, these are the problems with the James Webb Space Telescope, is that there are unique engineering challenges that have never been solved before,
Yeah.
and they're having to solve them for the first time. And ideally, you only want to solve one of them per mission. In this case, they took on perhaps too many to solve all of them, many of them. There are more that can come in the future, and are having to solve them. And the delays come when it turns out the answer was more complicated than you thought. So
Yeah.
it is a absolutely expected that these things are going to have quirks when you build them.
And with JWST, the analogy that I keep having in my head is when you ask someone to come out and give you a quote on how long it's going to take and how much it's going to cost to replace some windows, they do the best they can, but it could be once they get the frame of the existing window off, they find a squirrel living in the wall. They find asbestos, they find who knows what. And the cost changes and the time changes. And with JWST, they found the squirrel, they found the asbestos, they found knob and tube wiring, and they found everything else that could possibly go wrong in building the telescope.
Right. That's how you discover how things go wrong, is by trying to do it.
Yeah.
And then things go wrong, and then you recover from the things going wrong.
Yeah.
And then you learn from your mistakes. And of course, the great problem, the irony, is that in many cases, you won't have to build that. You will never build that telescope again.
Exactly.
And so you've learned all these mistakes, you've learned all these lessons, but you will never get a chance to really learn from those lessons, because now it's too late. You built your spacecraft, and now it's time to come up with a whole new technical challenge.
Yep.
So, yeah. Yep. Come on, James Webb, launch.
So 2 more minutes. Do you want any more questions, or do you want to just share all the things that people can do to get more involved with us and with Astronomy Cast?
I think I like your second answer there. One thing, and maybe someone can post the text in there. Okay, so we're doing a giveaway. Hold on.
So
we're doing a giveaway with the Weekly Space Hangout crew for the book. The Weekly Space Hangout crew is giving away 3 copies of the book. And I apologize in advance that I don't have all of the details in front of me for this part of it. But if you go to the wshcrew.space, they'll have more information about how you can win one of the 3 copies of this book that we're giving away. The end date is October 30th. So we're going to be, Dave Dickinson and I are going to be guests on our own show to talk about our own book. And so that's going to be coming up. So here you go. You need to send an email to giveaways@wshcrew.space with the subject UT Ultimate Guide, and include your name and email, and then we'll pick some random names and hand them out. And you've got, I believe, until the end of day on October 30th, but someone in the chat can tell me if I'm wrong. You,
And
what have you got?
well, and as a reminder, it is my turn to get to travel with Dr. Paul Matt Sutter. So join me on a tour of the American Southwest, which is a part of the world that's near and dear to my heart. We'll be visiting major observatories and some of the most amazing landscapes our nation has to offer. There's a lot of ugliness in the world. The American Southwest is not part of it. So come share cosmic stories with me and find out more by going to astrotours.co/starstrider.
Awesome. Just came back from the one in the Caribbean, and I had so much fun. And I was like, Paul, let me know when I can do another one. So we're already talking about future ones that I'll be able to run as well. So it was a good time.
Awesome.
All right. Well, thanks everyone. Thanks, Pamela. As always, thanks for engineering this week while I'm on the road. And everybody, we'll see you all. I'm not sure what the schedule is next week, but I'm sure we will announce it when we know it.
Okay. I will see
All
you
right.
all later. Bye bye.
Thanks, everybody.